All right, so again, here are your test content for tomorrow's test. There will be a f prime derivative graph. What you just picked up, worksheet 6, has 2 examples of the type of problem that you're going to see. So we'll do that today. We'll practice another optimization problem from the worksheet 5 you picked up yesterday. Was anyone not here yesterday? Didn't get a worksheet 5? Didn't get that. Okay, so we'll practice optimization problem. Curve sketching problem. This is like page 1 and 2 in your test review packet. We worked on that at the end of class yesterday. And then mean value theorem, Rolle's theorem, extreme value theorem, first derivative test, test for concavity, second derivative test. There will also be 3 problems, very similar to what you experienced on the quiz, showing up on the test. Okay. Okay, so let's start off with a derivative graph. The worksheet that you just picked up. Oh, before I forget, there is a slight typo on page 2. The range should be from -3 to 7. You can make that change. Range should be from -3 to 7. Okay. So your your test tomorrow will look like this problem where you'll be given an f prime graph. You'll be asked to create sign lines for f prime and f double prime. And then you'll be asked to sketch the original function graph, and you'll have some anchor points provided for you. And then the range will tell you, after everything is said and done, what should be your highest and lowest y values. And then you're going to sketch your f double prime graph. The only thing that I left off of this is information about where the graph is increasing, decreasing, relative max, relative min, all the because statements. But I'm assuming that we're pretty good with that. You can just read that off of your sign lines. You guys demonstrated your knowledge pretty well on the quiz, so we're just going to focus on the parts that I think we need practice with. Okay, so. Okay, so start off, let me this is the table that kind of helps us map out what we're looking at. Okay, so first we want to create our f prime sign line. We know the x-intercept is what we're after because the x-intercept is going to end up looking like a potential max and min on the f of x graph. So let's label accordingly here. If we're looking at f prime graph, then our y-axis represents slope values of the original function. So let's pick out our critical points. So 2, 4, and 6. Okay, let's look to see where the graph is located. Don't look at the rise and fall of the graph. Look at where it's located. If this is it above or is it below? If it's above, it represents positive slope of the original graph. If it's below, that means these are all different variations of negative slope on the graph. So from 0 to 2, where do we start? Where's this located? Yeah, negative. So negative slope. From 2 to 4, all this is clearly above the x-axis, so positive slope. From 4 to 6, negative slope. From 6 to 9, positive slope. Okay. Next up, let's create our f double prime sign line. Now we're trying to pull off concavity information from the f prime graph. So if we're trying to find concavity information, I first want to find points of inflection. So if I want to find points of inflection of the original graph, it's going to end up looking like the max and min of the f prime graph. So I'll highlight those points. The peaks and valleys of your f prime graph is where the original graph is going to be experiencing the maximum and minimum steepness, and the max and min steepness is going to translate to concave points of inflection on the original graph. So 1, 3, 5, 7, and 8. So now we look at the slope. Okay. The slope of the f prime graph is going to translate to concave up or concave down. So let's see if we remember. Negative slope on the f prime graph means what? The original graph is going to experience what? Concave down. Positive slope on my f prime graph indicates that my original graph is going to end up looking like what? Concave up. Negative slope would indicate concave down. Okay, it's going to keep flipping here. We were doing the handout that just picked up. Okay. I just want to help convince you that the slopes of the f prime is going to translate to either concave up or concave down. So imagine a concave up graph that looks like this, right? And imagine I just want to just do a ballpark slope values. This is -3, then -2, then -1, then 0, 1, 2, and 3. And you see how all these y values are increasing? So you can imagine these values could correspond to these values, right? That's a f prime, a slope value of -3, -2, -1, 0, 1, 2, 3, -2, -1, 0, 1, 2, 3. So a positive slope on the f prime graph. These are all slope values, and if I have slope values that are increasing, it's going to end up looking like a concave up. Okay. Meanwhile, if I have a slope that is +3, 2, 1, 0, -1, -2, -3, then that's going to end up over here, right? Slope of 3, y value of 3, y value of 2, y value of 1, 0, -1, -2, -3. So the fact that my slope values are decreasing, it's going to end up looking like this, which will translate to concave down. Are we good with the sign lines? I think this is the most important part of the problem, because if you don't have this down, then it's hard to get your function and your f double prime graph to look the way it's supposed to. And also, everything is building off of these, right? Because you're also grabbing your increase, decrease, relative max, relative min, points of inflection, all off these sign lines. So this is the most important step of the problem. Any questions here? Okay, next up. we're going to sketch our f of x graph. And my suggestion is find a way to cover up your f prime graph, because it's going to end up throwing you off if you're looking at this trying to graph your f of x. Okay, so if we cover this up, we have no need for this anymore. All we need are these notations and our indicated order pairs and range to help us sketch our graph. This curve is no longer going to be helpful. Okay, so I'm going to cover it up. All right, so f of x. We have some anchor points here. So 0, 1, and 9, 5. We can go ahead and plot those points. Okay. We do have the range to think about, that after everything is said and done, our highest y value should be 5 and our lowest y value should be -2. But we're just going to follow the path of the arrow. And if the graph is falling, we want the graph to decrease. If we have an arrow that's pointing up, we want our graph to increase. So what do you expect that to here? A relative what? Minimum at 4, relative max at 6, the relative min. So our graph should exhibit those behaviors. So I want my graph to decrease until it hits a minimum somewhere at 2, rise to some maximum at somewhere at 4, fall to some y value at 6, and then rises after that. So let's see if I can sketch the graph. I'm just doing dotted lines here. I'm not committing to the curvature of the graph just yet. So I'm following the graph here. It needs to decrease until I hit some y value, relative minimum at 2. Rise, it's a relative max, some y value at 4. Falls, it's a relative min, some y value at 6. And then rise until it hits my endpoint. Okay. Along the path of your graph, you're going to plot your points of inflection. Now, your points of inflection may be a different y value than mine. It's okay. We just want to, wherever your graph lands, you can just highlight that point. So there's a point of inflection at 1. So wherever your graph lands at 1, highlight that point. Point of inflection at 3, at 5, at 7, and at 8. So now I'm going to retrace my graph with the proper curvature that I'm expecting. So I want concave down to begin with, from first dot to second dot. Next up, from 1 to 3, concave up. From 3 to 5, concave down. From 5 to 7, concave up. From 7 to 8, concave down. From 8 to 9, concave up. Okay, let's double check that we have our range correct. Our lowest y value should be -2, so I'm just going to make this a -2. My highest y value should be 5, so that's consistent. There's my range. Next up, let's create our f double prime graph, f double prime graph, is going to be purely based off of your sign line. That's all we need. And we know that our points of inflections off of the original graph is going to end up looking like the x-intercept of my f double prime. So I'm going to label accordingly here. Above the x-axis is where my original graph is going to exhibit concave up. Below the x-axis is concave down. On the x-axis are potential points of inflection. And these are all x-intercepts, right? 1, 3, 5, 7, 8. Okay. Don't look at the shape of the graph, look at the location. Where do we want our graph to start? Above or below the x-axis? Below. And then I'm going to have these points here. So I know that my graph has to go through those points. It has to kind of thread through those points there. So I'm going to start below. So if I start below, I got to go up because I got to hit that point. And then from 1 to 3, concave up, that's correlates to above the x-axis. So it's just going to go above, come back down, below, come back up, go up. And then finally, after 8, it's going to end up above. Don't match the shape. The shape is not, this concave up, concave down shape is for the original graph, not for your f double prime. Okay. How do we feel about this? So now that I've done one with you, I'd like for you to try one on your own. I want to walk around and see, can we get our sign lines? Can we sketch our function? Okay. And again, there's a slight change. If you came in late, the range should be from -3 to 7, not -3 to 5. So when everything is said and done, your original function graph should have a lowest y value of -3 and a highest y value of 7. I'll leave this up here so you can use this as a help you remember what we did. Thanks. All right, thank you. I'll leave number 1 on the projector so you can use that as reference. there's no peaks or valleys in two, so two is not. There's no peak or valley, so that's what we see is a flat. Zero as well. Zero is also yeah. There's no shit, but it does flatten out for a moment. So yeah. Zero as well. There's no change in size, but it is still that. So it kind of helps your graph. Flatten out. Okay. Increase the slope. Yeah. That works. It's here as well because it is X intercept. There's no change in sign. It does tell you that your graph is flat down or so. And look at the slope. We're going to slope up here. That prime slope factor to so this is negative slope. It's not getting positive. It's not getting so we don't do that means like we want to be about this. This 19 here is a and I just like I just like so I can just read just that yeah, control that like computer. Once you build your sign lines, try to cover up, find a way to avoid looking at your F prime graph because that's just going to end up confusing you. So walking around, your sign lines look great. So that's a good start. Okay. Once you have your sign lines, that's all you need to build your graph. We want our graph to rise from our starting point, hit a relative max at negative 1.5, falls. We do want to, some of us were leaving 0 out of your sign line. You still want that 0 on your sign line, even though there's no change in sign, because it does tell you what's happening. The graph is flattening out for a moment before it decreases again. So we do want the graph to level off at some y value at x equals 0. Falls, hits a relative min, and then rises again. Now my range is from -3 to 7, so I know that my graph is rising. This is going to have to be the highest y value here, and then the lowest y value should be at 2. So because I know that my endpoints are set, so those aren't going to move. So it has to be the relative max and relative min that's going to end up causing the max and mins of my range. From here, go ahead and highlight your -1, 0, and 1 wherever they land, and then you're just going through and marking, shaping your graph with concave up, concave down. Second derivative graph, you're just building it off of your F G double prime graph. -1, 0, and 1 should be as your x-intercepts. And then don't look at the shape, just look to see where it needs to land. Between -2 and -1, it needs to start off below the x-axis, link up to this point of inflection, then above the x-axis, then below, then above. Okay. There's another one of these practice problems in worksheet 5. So if you haven't done that one already, I think that could be a good final practice for you to do later today or tonight. But from what I've seen, looks like you guys are pretty good with your, at least with your sign lines. I didn't see your graph, but hopefully you can keep reminding yourself that your graph should look nothing like your G prime. So they should, all three should look distinctly different from each other. Okay. All right, let's go to worksheet 5, what you picked up yesterday, and let's do an optimization problem. So page 5. If you're here at the help session, just try page 6 then. So page 5 and 6 are both optimization problems. If you're here for the help session this morning, try number 6. You guys have the key to get some quicker. Off yesterday's handouts. Okay, go ahead, try this. The box has a square base, so you know that the length and width of my base are the same. I can use the same variables there, x and x, and then use a different variable for my height, h. Volume is going to be my supporting equation, 30 equals x squared h. Surface area, this is an open top, so I have 5 sides. I need to, 5 surface areas I need to account for. So there's the base area, which is x squared, and then each of the vertical sides have area of xh. Once you have your surface area built out, you can multiply your cost of each uh, material into the each of the sides. So the base is the most expensive material, so 15 times x squared, and then the $7 needs to be multiplied in for all the xh's. Once you have your cost equation spelled out, you know that's ultimately where your derivative is going to have to be involved. So we have to find derivative for cost, but we need to resolve the h. So go to your volume equation, make that substitution, get your cost equation down in terms of x, then clean it up, get it ready for power rule, find the derivative, critical point, solve for x. And then when you solve for x, you're pretty much near the end of your problem. You just have to go back and see what else the problem is asking you to find. So once you solve for x, the dimensions, length, width, and height, the length and width are the same. So I'm able to use the same x values twice. The height is 30 over x squared. So I'll plug that in, get that value. Surface area, the exact point surface area, just plug into your surface area equation before the dollar amounts gets multiplied in. That will get you your value there. And then cost, any of those cost equations can help you get to your $440. Just make sure you don't plug into C prime. Okay, any questions here? Okay, on the same worksheet 5, can you turn to page 3? I just want us to try number 9 here. Page 3, number 9, bottom of the page. Remember the chart that we've been doing here, the XMPs. I do want to point something out that if you're looking at the second derivative graph, you do want to look at your x-intercepts because these are going to be the places where your potential points of inflections are. But I want to say the word potential because it's only a candidate if it hits the x-axis. It needs to do what in order for this candidate to be a point of inflection? There has to be a what? Change in signs. So if it hits the x-axis, it doesn't mean that it's a guaranteed point of inflection. So start off by creating your concavity sign line. Above is concave up, below is concave down. You're going to see that not every x-intercept has a change in sign. So not every candidate is going to be a point of inflection off of the original graph. This is a worksheet 5, page 3, number 9. Okay, so the only points of inflections we see are where? Which points? D and E, yeah. So I is an x-intercept, but it doesn't change signs, so it doesn't do enough for it to be a point of inflection. So the graph starts off above the x-axis, concave down, then below, concave down, then above, concave up, but then still above, concave up. So there's no change in sign at I, so points of inflections only at C and previous page. Number 6. This is second derivative test. What can we conclude about what's happening at 5? Relative what? Max, yeah. I know that this problem, this number still kind of causes us some issue because we want to associate that with a low number. But maybe here's another way to think about this is what if this was in terms of position, velocity, acceleration, right? So position would just be where the graph is, right? Velocity, velocity 0, and then this would be quote unquote negative acceleration. So if you imagine a ball being thrown up in the air and eventually makes its way down, right? Eventually it's going to hit a velocity 0, which in this case we can think that f comma 5 equals 0 as velocity 0. And here, I think this is negative acceleration. So negative acceleration is where your velocity is decreasing, right? So positive velocity, positive velocity, positive velocity, velocity 0, negative velocity, negative velocity, negative velocity. So this is causing my graph to experience a negative acceleration. So if you think of that as negative acceleration, you can visualize, okay, my slope, my velocity is eventually decreasing. Meanwhile, if f double prime of 5 is equal to 26, think of this as positive acceleration. Positive acceleration means my velocity is increasing. So negative velocity, velocity 0, velocity 1, velocity 2, velocity 3. So think of that as, or slope, right? Negative slope to positive slope. This would indicate concave up or therefore relative nip. All right, so yeah, I have all these problems kind of spread out across different worksheets, but just want to make sure that we know exactly what to expect on the test. We've been kind of circling through these problems over the past few days, so hopefully you guys feel better with all the concepts that we've been reviewing. All right. Half help session tomorrow, 7:10 to 7:45. I'll also send out a link if you want to join virtually. Okay, I can read the phone. Test tomorrow. You can bring your calculator. Right. It's more like going to be on a within the context of this where you have to create your slope and have this online. So that's just additional practice. Okay. Thank you.
Excuse me. Apparently I just absent.
Oh, sorry.
Okay.
I thought I changed. Let me check.
No, you're good.
Okay.
Thank you.
Great. Mark it down. Thank you.